Good morning and greetings to everyone attending the West Australia Mining Virtual Conference, Day 2. I'm Ian Burrell, the Managing Director of Control Systems Technology, and we specialise in the manufacture of high accuracy belt scales. Today, I'm presenting a case study of a recent installation in South America. On a recent visit to a copper mine in South America, we learned of an accounting problem at one of the many large copper mines there. The mining company had no confidence in their existing belt weighing equipment and asked if we could help. Actually, as soon as I saw their conveyor, I knew they had a problem with belt weighing. Their conveyor was very long, with high lift, and the belt tension had to be very high and variable, a real nightmare situation for an accurate belt scale. The mine personnel said that they were at their wits' end with the equipment. It was apparent that they were not getting any assistance from the supplier. We were invited to analyse the existing equipment. The conveyor is 473 metres long with a lift of 71 metres, and due to a vertical curve, the belt scale was located 253 metres from the tail at a vertical lift of 25 metres. At the belt scale location, the belt tension is 31 tonnes. This is a very difficult location for a belt scale. To illustrate the difficulty of the location, note that given the 1,000mm idler spacing, it takes 31 kilograms of weight on the conveyor to deflect the belt by 1 millimetre. Since the weigh frame only supports about 2,000 kilograms, this would represent an error of about 1.6%. The customer belief was that the belt scale had a bias or systematic error of up to 4%, and this is a long way out for a 0.25% system. So, as requested, we subjected the existing belt scale to our engineering analysis. We interpret three components of belt tension: fixed, load variable, and random, and we interact them with three components of belt scale misalignment: fixed misalignment from the installation standard, load variable misalignment from weigh frame deflection under load, and random misalignment from roll out of round. Our calculated error was 1.7%, in the order of 10 times worse than the customer's expectation. We were also requested to design the alternative equipment, which actually had to be located even further up the conveyor in a still worse location, so that the existing scale could be compared. We ended up proposing a 4-idler scale, with each idler set spaced at 4,500 millimetres, some 4.5 times longer than the standard spacing on the conveyor. This would be a highly unusual custom-designed belt scale with a weigh length weight of 10 tonnes, 5 times more than the existing scale. The new unit, taking into account the weigh frame weight and the long idler spacing, is more than 20 times more stable than the existing unit. But 4,500 millimetre spacing, how is that possible? The fact is that if belt tension is very high, then idler spacing can be very wide, depending upon roller bearing size, of course. However, CST has a patented design which facilitates long idler spacing by providing very good belt support. This is our close-spaced roller rack, or CSRR, as shown. The belt has extra horizontal rolls between fully winged sets, in this case spaced at 4,500 millimetres. The CSRR combines the benefits of good belt support and long equivalent idler spacing. At the same time, wing roll loading is acceptable, and we have years of experience to show that the system works well. And this is the unit we proposed to the mining company: a relatively large belt scale with 10 tonnes of calibration mass and a weigh length of 18 metres. Definitely a sizable unit. It has to be supported on 4 load cells, each with its own little hip roof. All of the 4 full idler supports has 2 calibration masses of 1.25 tonnes each. We were able to get an order for this equipment. However, we had already been thinking about ways to improve the design. The first proposed weigh frame design had very low deflection at the ends, but more deflection near the middle, and the steel sections were likely to make maintenance difficult. So we revised our design midstream and ended up providing a symmetrical pair of belt scales with very small deflection at the far ends and less deflection in the middle than with the previous design. Our system now had 8 load cells instead of 4 and could be configured either as one scale or as a dual redundant pair. So the alternative design is much more open and maintainable. It has the calibration masses applied directly to the idler sets. Each mass is split to allow a 50% linearity test. We did not linearize against static mass. We only linearity test to prove waveframe health. The design has the added advantage of offering dual redundancy, and the wade-to-wade transition between the two waveframes is an errorless internal force. The CST electronic system is able to accept 8 load cells, either as 2 individual inputs or grouped as one belt scale. We retain the option to configure the system as one belt scale or a redundant pair. As you can see on our electronics, there are 2 independent sets of terminals for the 2 waveframes, and each is also able to have its own tachometer. And this is what the front panel looks like. This is the remote display captured from my own PC in Sydney via a 3G modem from site. Each bell scale has its own display and setup data. We have complete remote control for maintenance and troubleshooting via a secure VPN tunnel and a custom PC client. So we put the order for this equipment through our Revesby, Sydney factory, where we produce both mechanicals and electronics. Here the project is seen at the first trial assembly stage, and the system is assembled again after surface finishing, which in this case was galvanizing, and then is performance tested with its own electronic set. And finally, it's time to pack the system into a 40-foot container. The equipment was delivered to a South American port, unpacked out of the container, and trucked to site, whereupon it was again assembled into modules for lifting into place. The equipment was removed from the container at the port, and we were pleasantly surprised to find that all the parts made it to site intact. This was quite an important installation for CST, and we normally provide our own installation supervision team. This is a large job and time was short, so it seemed that at least 2 of our technicians should be available at all times during the 48-hour shutdown. There was an argument for at least 4 people to cover the 24-hour operation. In this case, we provided 5 of our Australian citizen specialists, including myself. First, we all had to have 6 days of safety inductions on top of a 2-hour medical, which checked everything from blood type to intelligence. The inductions were interesting since they were conducted totally in Spanish, and we had to pass 2 tests every day. Fortunately, 2 of our team speak Spanish, and we managed to pass the tests. The inductions were necessary, otherwise we'd not have been able to be within 1 metre of the conveyor, and otherwise we could not have made any manual adjustments ourselves. Then to enter site, we had to have our tools catalogued. The rule was that everything we took on site, whether an iPhone, a computer charger, mouse, screwdriver or spanner, could not be taken off-site again unless it appeared with serial number as appropriate on a signed-off list. It is actually much easier to work on Australian sites than in South American sites. The installation was conducted over 2 consecutive 48-hour shutdowns. The safety standard was extreme, even to the extent that anyone working in our own cubicle had to wear special electrically rated boots. But some aspects, such as fatigue management, were less stringently controlled. Our team were mainly concerned with the all-important alignment, and while there was considerable communication and coordination problems, we got the job done. Commissioning and calibration came at the end of the second shutdown and was relatively uneventful. The 2 halves of the system were calibrated completely independently. There is no plan to recalibrate the system in the short term, since the calibration will be stable for years. The system became operational early December 2019. We were lucky to have timed this work before the outbreak of COVID-19. Since commissioning, we've been able to remotely monitor the system via a secure VPN connection. By way of summary, these are the extra benefits which we provided to this customer beyond their initial requirement, which was simply for a 0.25% belt scale. The symmetrical dual redundant system is a form of built-in quality assurance. Since the two halves are not fudged to agree, they continuously demonstrate the quality of the installation and provide confidence to the customer that there is no bias error. This is a record of the agreement between the two halves of the system. The data was remotely gathered from the audit trail and captures the totalizer as it was reset every day. This data shows that the two halves of the system consistently agree in the 0.06% region. This is acceptable for a 0.25% belt scale and is a holistic record of total system health. There is some noise in the data since some days had very small deliveries, and also no provision was made for the amount in transit between the two wayframes. I want to repeat that the calibration of this system will remain stable for several years without adjustment. As a matter of further interest, some interesting data about belt wear can be extracted from a stable belt scale like this one. The above graph shows how the conveyor belt is becoming lighter with wear. It's losing approximately 0.5 kilograms per metre of length per month. This information is useful for predictive maintenance, and this data was captured remotely from the automatic zero tracking log. This concludes our South American adventure. The customer now has a belt scale that they can have faith in. If you have any questions, please ask them now or send me an email.